Hello. In my paper with John Goes, towards an average version of the Birch and Swinnerton-Dyer Conjecture, we investigate the distribution of normalized zeros in one-parameter families of elliptic curves of rank R over Q of t. According to the Birch and Swinnerton-Dyer Conjecture, if the Mordell-Weil group of the elliptic curve has rank R, then the associated L function should have at least R zeros at the central point. Mester proved that given an elliptic curve, if you go up a certain height on the critical line, you are guaranteed to see at least one zero. What we consider is instead the related question of, consider for a family of elliptic curves and a given interval on the critical line, how many zeros on average, how many normalized zeros are on average are in that interval. The main tool, similar to Mester, is using the explicit formula, or equivalently the one-level density for the family. The explicit formula relates sums of a test function phi at the zeros of the elliptic curve to sums of the Fourier transform of phi at primes multiplied by the Fourier coefficients of the elliptic curve. Ideally, one would like to choose an arbitrary test function phi. Unfortunately, we're only able to do the calculations on the number theory side with the sums over primes for phi suitably restricted. Our main result is that assuming we can work with test functions supported, whose Fourier transform is supported in the interval minus sigma sigma, then the number of normalized zeros in the one-parameter family of elliptic curves of rank R is at least R plus a half, and so this is number of normalized zeros in the interval negative 1 over 2 sigma, 1 over 2 sigma, and that's less than equal to pi squared over 4, R plus a half plus 1 over sigma. Ideally, we would like to take our test function to be the Dirac delta function, which has support basically 0, and that would tell us exactly what's going on at the central point. Since sigma is the support of the Fourier transform, so equals minus sigma sigma, if we were to take our test function phi to be the Dirac delta function, then its Fourier transform is the constant function 1, and in that case sigma would be infinity. If we were able to prove the explicit formula results, if we were able to analyze these sums, if we were able to study the one-level density for the Dirac delta function, then we could take sigma equals infinity, and we would know exactly what's going on at the central point, and this of course would be the Birch and Swinnerton-Dyer conjecture. Unfortunately, typically the best sigmas are somewhere between at most 1 and roughly some constant over the degree of the polynomial of the conductor. If you consider the random matrix theory predictions for how many normalized zeros there should be in this interval, you do obtain a number that is between R plus 1/2 and pi squared over 4 R plus 1/2 plus 1 over sigma. So the answer we get is still consistent with random matrix theory predictions. Thank you.